Good morning to all of you. So in the previous demonstration, we were able to simulate a simple reactor model known as R-stoic and saw how to calculate the standard heat of reaction. Now in the same way, I would like to demonstrate using the same model how we will be able to calculate the adiabatic reaction temperature. In your thermodynamics course, you are aware of how to calculate this adiabatic reaction temperature and what is involved in calculating this particular value and the kind of information and complexity. Now let me demonstrate this using Aspen. Now as is the case, the first step is to define the components involved in the problem: carbon monoxide, hydrogen, and then methanol. So having defined the components, the next step is choose a property model. Let me choose Java Cedar. Go to next. Go to simulation environment. So click on reactors tab, choose R-stoic model, connect input and output streams. And then product. There are two reactants and one product. As is the case, this is meant for water decant, which is not mandatory. So having drawn the flow sheet, now we'll be able to go into the next input screen. As is the case with any rating model, we are supposed to provide information with respect to the input streams and blocks. Now this is the given information. The reactants are entering at 25 degrees centigrade, a pressure of 1 atmosphere. And let me assume the flow rate of CO as 1 kilomole per hour. Now this is with respect to one reactant. Because there is only one component involved in the stream, now we were able to satisfy the degrees of freedom. And we have given the required information with respect to stream 1. Say next. Now this is with respect to stream 2. Again, the temperature is 25. Pressure is 1 atmosphere. Earlier, having chosen a flow rate of 1 kilomole per second, 1 kilomole per hour of CO, now the flow rate of hydrogen should be 2 because CO and hydrogen are entering in the stoichiometric ratio. Once again, we were able to satisfy the specification for stream 2. So go to the next input screen. Now this is the information required with respect to the block. Earlier, when we were trying to calculate the standard heat of reaction, we were able to mention the temperature and pressure. Now, we are required to calculate the adiabatic reaction temperature. So instead of temperature, choose duty and select the duty as 0. In other words, I am specifically suggesting no heat should be either added or removed from the system, that is the reactor, when the reaction takes place. Let us once again consider the reactor is operating at 1 atmosphere. Now, we are still required to specify what is the reaction that is happening. So say next, new, choose the reactants and products, carbon monoxide, stoichiometric coefficient is 1, hydrogen, stoichiometric coefficient is 2, and then the product is methanol, stoichiometric coefficient is 1, and the fractional conversion has been given to be 0.8. with respect to CO. Now we were able to satisfy the, specify the reaction. Close this window, go to next input setup. So we have completed the problem definition. We will be able to run the simulation. Yeah, now you can see the stream summary. So the reactants are entering at, both of them are entering at 25, whereas the output is leaving at 949. Why this increase in temperature? In the previous case, the reaction was considered to be exothermic. So the heat liberated is not being removed. So hence the heat liberated has to be consumed by the product stream. So remember, the total product leaving the reactor happened to be 1.4 moles. So much of heat has to be absorbed by this product stream, thereby the temperature is increasing up to 950. Now, if I go back to the problem statements, now you can see the third problem. Now, what will happen to this adiabatic reaction temperature in case if CO versus hydrogen is 1:10 instead of 1:2? Now, what do you expect will happen? I'll go back and change the problem statement. Click on hydrogen stream. Earlier we specified this as 2 because the flow rate of CO happened to be 1. Now the ratio is 1:10. Once again, let me run the simulation. Now look at the results. Now what is the total number of moles leaving the reactor? 9.4 instead of 1.4 in the earlier case. Now what happened to the adiabatic reaction temperature? It came down to 271 from 949. In fact, the excess reactant, that is excess hydrogen, is going to control the increase in temperature. In other words, this may be acting as some kind of a diluent. In some cases, if there is a tendency for the temperature to shoot up, such a diluent is made use to maintain a proper control over the increase in temperature. But remember, this could add to your penalty. The product stream, from the product stream, the excess reactant or the inert that is added to control the temperature increase may have to be separated. This may increase your separation costs. Now, we were able to calculate the adiabatic reaction temperature by specifying there is no heat input nor output when the reaction is in progress. Depending on whether it is exothermic or endothermic, there could be either a temperature increase or temperature decrease. Now, in this way, we should be in a position to calculate